Okay, chapter 31, wave shaping circuits. This is the last chapter of the analog circuits section, and after this we're going to be getting into digital, and I'll give you an introduction to digital when we get to 32. So this is our last analog circuits chapter. And actually, some of this content is going to be a review as you've been exposed to some of this material already. Wave shaping circuits. After completing this chapter, you're going to be able to identify ways in which waveform shapes can be changed. Explain the frequency domain concept in waveform construction. Define pulse width, duty cycle, rise and fall time, undershoot, overshoot, and ringing as they relate to waveforms. Explain how differentiators and integrators work. Describe clipper and clamper circuits. We will not, however, be discussing the clapper. That's something different. Describe the differences between monostable and bistable multivibrators, and draw schematic diagrams of wave shaping circuits. A non-sinusoidal waveform is a periodic waveform that has the same waveform for all cycles. So that means it's something that repeats itself, and in repeating itself, it is an exact copy of what was original. So as long as it repeats itself, you could time that and add a cycle to it. Now, according to the frequency domain concept, all periodic waveforms are made of sine waves. Just different combinations of sine waves added together. Sine waves are the only waveforms that cannot be distorted by RC, RL, or LC circuits. So what that's saying is when we feed it through these circuits, it's not going to distort it. The sine wave that has the same frequency as the periodic waveform is called the fundamental frequency. So that's your original frequency. So if you could go ahead and take a look at a periodic waveform, a sine wave on an oscilloscope, time that waveform, establish the period of that waveform, take the mathematical reciprocal of that, you end up with the frequency. That frequency is the fundamental, what we call the fundamental frequency. Not to be confused with harmonics. We're going to talk about harmonics in a minute. So what we're looking at in this illustration are actually two cycles of the sinusoidal waveform. I'm looking at a total of 4 alternations, right? 2 positive alternations and 2 negative alternations. A positive alternation and a negative alternation make up 1 cycle of a sinusoidal waveform. In illustration B, we're looking at a square wave. What makes it a square wave is that half of the time it's on, half of the time it's off. If it's anything other than 50-50, it's not a square wave. If this pulse is less than 50%, we call it a pulse waveform. If this is greater than 50%, we call this a rectangular waveform. But if it is exactly 50%, we call it a square wave. Below this is a triangular waveform. Excuse me, this is a sawtooth waveform, not triangular waveform. Triangular waveform would have a rise time and a fall time that are equal. This has a long linear rise time and a short linear fall time. That makes it a sawtooth wave, not a triangular wave. Now, harmonics is the fundamental frequency. First harmonic is a harmonic nonetheless. So the fundamental frequency is known as the first harmonic. Harmonics are going to be multiples of the fundamental frequency. They can be combined in an infinite number of ways to produce any periodic waveform. So in this particular example, we see the first harmonic here is 1,000 hertz. So this is like a 1 kilohertz frequency. If the fundamental frequency is at 1K, the second harmonic is going to be 2K. The third harmonic, 3K. Fourth, 4K. Fifth, 5K. See the 22nd will be 22K. They're going to be exact multiples. And these harmonics will really go on to infinity. It's like if you're at a lake and you throw a rock in the lake and it sends out a wave and then the waves come back. They just keep getting smaller and smaller and smaller. It's the same thing with harmonics. Harmonics really go on for infinity. But eventually they get so small that they're not really an issue. What we're looking at here is how a square wave is made up of the fundamental frequency plus an infinite number of odd harmonics. So what we see here is our first waveform. That's our fundamental frequency. That's the hash mark line. Everybody see that? So we get that, and then we start picking our odd harmonics. So our fundamental frequency is our first. Our next odd is going to be our third harmonic. If I add my third harmonic, this is what's in blue, the light blue right here. Algebraically, if I add my first harmonic and my third harmonic together, I'm going to get a waveform that looks like this solid black line right here. This kind of looks like some kind of a tooth or something. But that's with my fundamental and my third harmonic added together algebraically. If I get my fifth harmonic and add it, my fifth harmonic now is going to be this blue waveform. If I add that to my first and third harmonic, now I'm going to get this waveform. If I get my seventh, my ninth, what eventually is going to happen is this is going to clean up and this is going to look like a square wave. Yes?
So oscilloscope, how many harmonics does it usually add together to get that signal? You said it's infinite, so it's got to cut off somewhere, right?
Right, and to be honest with you, the quality of a frequency generator is going to be based on how clean of an output you actually get. So when you look like at our function generator, not the oscilloscope will monitor this, but actually what generates this is our function generators in there, the Kenwood models. And what that's going to do is it's going to generate this square wave, and the more expensive the unit, the more it's going to take into consideration and give you a really nice, clean, crisp square wave. But basically every square wave is going to be made up of these harmonics. If you have a cheaper one, it probably is not going to add as many of those harmonics together to give you that square wave. Because obviously adding an infinite number, at what point are you throwing money into a black hole? How important is it? And actually for some electronic systems, you know, like if an engineer needs a square wave, how much money are they willing to spend on a circuit that's going to give them the perfect square wave? And at what point you reach a point of diminishing returns? You know, like, yeah, I'm throwing all these parts at it to make it so I get a perfect square wave. Well, you really don't need a perfect square wave. You need something that only kind of looks like this, if that's what you need. That's what specifications are all about. Good question. A sawtooth wave. Sawtooth wave is a very popular wave that creates like the raster in a CRT display. or on a radar display. It's what actually pulls the electron beam horizontal from left to right. Sweep generator inside an oscilloscope is nothing more than a sawtooth generator. So to make the sawtooth generator consists of the fundamental frequency plus even and odd harmonics crossing the zero reference line 180 degrees out of phase with the fundamental. So here we take those harmonics, invert them 180 degrees, and then add them together. So what we have here is the fundamental frequency. When we add the second harmonic, look at just adding the second harmonic 180 degrees out of phase gives us something that already that looks kind of like a sawtooth wave. When we add the third harmonic, which is in phase with the fundamental frequency, now we end up getting this. The fourth harmonic with the even harmonics 180 degrees out of phase, now we get this resultant waveform. And then finally, as we continue to add an infinite number, we end up with a waveform that looks like a sawtooth waveform. And what may appear to be a sawtooth waveform on your oscilloscope, when you really zoom in on that, you may see that there's little ripples there, and it's actually made up of these different waveforms. One of the ways of looking at this as well is if you look at this on a spectrum analyzer. An oscilloscope looks at time versus amplitude. A spectrum analyzer looks at frequency versus amplitude. So if you get a square wave and feed a square wave in, what you're going to see is that original fundamental frequency, and then you're going to see all of those harmonics that make up that square wave. You look at it on an oscilloscope, looks like a square wave. Look at it in a spectrum analyzer, you're going to see the fundamental frequency and then all those harmonics that make it up. Same with any of these wave patterns. Now, a period of a waveform is measured from any point on one cycle to the same point on the next. Probably the best way of showing you this is on the whiteboard. As nice as they like to draw stuff in the book, this is what you're really going to see out in industry. Actually, it's not even going to be this pretty. One of the hard times that I had was in the military. I'd get these beautiful tech manuals that had these artist depiction of what the waveforms are supposed to look like. And then I'm out in the fleet and I'm looking at stuff like this and like, this doesn't look anything like, you know, in the book it looked like this, you know. I mean, is there a resemblance? Not really. So I really struggled with this, the world of reality versus the way the world of an artist depiction. The nice thing now is actually back in the day, some of the more expensive tech manuals would include a physical photograph of the face of the wave pattern on an oscilloscope. But that cost a little bit more money to have an actual photograph in there. Now the nice thing is digital screen capture. You could export it as a JPEG file and slap it right into a document. For your project reports, you could hand in images of waveforms. And here's an actual waveform from my project, what it looks like. But you've got to be able to interpret this data. Now, they talk about the period of a waveform. So to identify a period of a waveform, you have to establish it could be any point to any other point. So I'm just going to assume right here, I'm going to pick this point right when I start to rise here. I'm going to say that this is the start of a cycle. Okay? tell me where the ending of that cycle is going to be. Let me know when I reach the end of that cycle. Exactly, very good. Okay, so all we have to do here is measure the amount of time that it takes to go from here to here, and that's going to give me my period. It's going to give me my period. The other thing that this time could be called, it could be called a pulse repetition time, PRT, or it could be called a pulse repetition interval. And the interval in electronics that we use as time measurement is the second. So it could be called PRT or PRI, and it represents time from the start of the waveform to the end of the waveform. From that, we could calculate out what's known as a PRF, pulse repetition frequency. And it's really easy to do. It is simply the reciprocal of PRI or PRT. Just like time to frequency, 1 over time is equal to frequency, 1 over frequency is equal to time. Same thing holds true here. So if any of you ever go to work on radar, commercial radar, one of the big things, one of the parameters that you're going to have to perform measurements on is going to be the pulse repetition frequency or the pulse repetition interval. Okay, it's something you're regularly going to have to do. This is a chapter that I'm actually passionate about because this is exactly what I used to do a lot of my time in the Navy. I used to analyze this. Not our radar, but other people's radar. And if I could look at that, I'd call this up on my equipment, and I'd look at it, and I'd figure out what the PRT is. Once I figured out what the PRT is, I actually had a calculator. It was in my operator position. I had a computer keyboard in front of me, a screen here, a screen here. There were a couple of oscilloscopes here, spectrum analyzers. But over here on Velcro, we had a calculator. And what the calculator was, the only reason we had the calculator was I'd plug in the pulse repetition interval and then go the reciprocal of, and that would give me the PRF. And the reason that I was using a calculator, I had on a computer screen what the computer thought the PRF was, but I didn't trust the computer. If you trusted the computer, you might kill a friendly. And I didn't want to trust it. I wanted to look at it, because if I'm looking at this, there's no way of faking it. If I perform that pulse repetition interval measurement and calculate that the PRF, then I could check my computer and make sure my computer's not bum doping me. Because the military, it's like life or death, so you can't make mistakes with that. And actually, how would the computer make a mistake? How do you think the computer would make a mistake? Anybody want to take a guess at this? It's something we've talked about already today.
Not reading the wave right, it looks like a perfect wave.
Elaborate more. It's actually an easier answer. It's a one-word answer. Harmonics. If you're sitting so close to an emission, that computer would pick up a harmonic and think the harmonic was the fundamental frequency, and it's not. The computer didn't know. The computer's only as good as it was programmed. So again, I wouldn't want to trust that. There's some stuff you trust, and if it's a quick scan, okay, yep, things look good out there. There's no real threats out there, but here's a target of interest. Let's really analyze this. Nah, I don't think that this is, this is what the computer says it is. So that's a pulse repetition frequency, pulse repetition interval. The pulse width is the length of the pulse. And what we're going to do is we're going to take this pulse width measurement. We're going to establish where 0 percentile is. Okay, so this is my 0 percentile. That's actually kind of low, but that's the artist. It's not the wave. Okay, so this is 0%. Okay, and we're going to establish 100% right up here. So halfway between 0 and 100 is going to be 50%. So at 50%, right at this point here, 50%, I'm going to take this measurement here, and I'm going to take this measurement here. And what this is going to be equal to, this amount of time, is going to be my pulse width. My pulse width measurement. So we're always going to take that at the 50% point. Now there's another number that's important for us to analyze when we're analyzing waveforms, and that's called duty cycle. Duty cycle is really easy. It's going to be the pulse width over the pulse repetition interval. The pulse width over the pulse repetition interval. And what that duty cycle is physically how long is this transmitting out? How long is that pulse actually doing something, as compared to how much time is the rest of the circuit at rest. So just by taking a look at this, let's kind of eyeball this. Again, this is a crude artist depiction, but let's just say, for example, here that, okay, that's about 19 inches, 20 inches. And then let's compare that now to the amount of pulse repetition interval. There's 1, 2, let's roughly call it 3. No, 3 times 20, so 60. 20 divided by 60. I was using that just as a reference. So basically, what would the duty cycle of this be approximately? If it's on for 20 inches and the total cycle is 60 inches, 1/3, very good. So this would have a duty cycle of approximately 33%, 33 1/3%. For some circuits like radar, it's critical. It's critical because what the radar system is doing is here, well, there's a bunch of things happening with the radar signal. Number one, here you're listening for that return, okay, because you're actually spitting out a pulse. And then you're listening for the return, how long it takes to get back. So actually, this is not a very good, well-designed radar. Okay, the signal's not going to get very far before you're expecting it to get back. But the other thing is, this is when it's building up that pulse, and then here it's spitting the pulse out. So you could tell so much about a radar, which again is exactly what I used to do in the Navy. By me looking at this, I could tell you what the radar would be used for. So we'd go places that we weren't supposed to be to basically look at what the Russians were doing. And then we'd pick something like this up, and then I'd have to analyze this and say, you know, this is a short-range radar. This is a short-range radar. And there was some other math I'm not going to bore you with, but we could actually execute. It was one of the fun, I actually taught this for the Navy. It was called an Operations Employment course. And basically what it was is when World War III starts, it's going to totally change a game plan. And if you encounter something that hasn't been created yet or that we didn't know about, how can you analyze it and make sense from an intelligence standpoint of what this is? So if this was a real radar, this would be a very short-range radar. It'd be a very powerful short-range radar. This might be for something like navigating in a river or tight-in area. But this doesn't give enough time for you to spit the pulse out and then listen to the return, because it's got to travel at the speed of light to the target and then all the way back. So this wouldn't be a radar that's designed to look at something 400 miles away. This would not be a radar that's going to detect a missile launch or something like that. This is something close in, navigation radar. So by looking at this stuff, you could tell what it's kind of used for. Make sense? And I'm not just talking about military radar here, so don't think, well, yeah, I'm not going to go into the military, I'm not going to use it. It's the same thing, whether it's sonar, whether it's a fish finder, whether it's a depth sounder underneath a ship, Whether you go to work for the Federal Aviation Administration and this is a radar system used for tracking aircraft landing at Seattle, the fundamentals of the electronic waveforms all remain the same, and that's what we're here to study. So that's our duty cycle. Pulse width, duty cycle, pulse repetition interval, pulse repetition frequency. The rise time is the next thing we're going to take a look at. The rise time is something that we determine from the 10% point to the 90% point. Basically what we do is we discount the first 10% of rise and we discount the last 10% of rise. So we're only paying attention to basically 10% to 90%. And what we'll do is we'll take a look at that reference in time, that reference in time, and I'm going to call this my RT, or rise time. And that's going to be in fractions of a second, milliseconds, microseconds, nanoseconds, whatever. Fall time, we're going to do the same thing. We're going to take a look at the 10% point. Remember, this was 0. This is 10. This is 100. This here is going to be 90. And this here is 10. So I'm going to take a look at this. Take a look at this. This distance between here, the fall, 90% to 10%, is going to be my FT, or fall time. Now just taking a look at this, that's my fall time. That's my rise time. We see that my rise time is significantly shorter than my fall time. And I drew it like that intentionally. I don't know why, but I drew it like that intentionally because I did the same thing. I tried to mimic that over here. Actually, this is a little bit steeper. But, yeah, this would be a little bit. But I was trying to accentuate that because sometimes there's idiosyncrasies in the circuits that cause this from happening. Sometimes your rise time, as you're building up the pulse, may take longer. Then the pulse gets spit out, and then it drops faster. I mean, it's idiosyncrasy of the circuits. The bottom line, the reason we're sharing this with you today is that you've got to be able to articulate that. You've got to be able to measure that on your equipment. You have to know what it looks like beforehand, and then you have to be able to, when you're troubleshooting the equipment, is this a problem or not? You know what this also could look like? This could look like a pulse width of a waveform being sent to a fuel injector to squirt gasoline into a cylinder. It could be the exact same thing. It's all done with pulses. It's actually, that would look pretty good for an automotive application going to a fuel injector. By playing with that pulse width, that's how much gas you're squirting in to your intake. That's rise time, fall time. Some of the other stuff we're looking at here, overshoot occurs when the leading edge of a waveform exceeds its normal maximum value. So you see how this is like my 0 reference line right here? This right here is going to be overshoot. It should have just gone right up. I mean, ideally, we wanted this waveform to look like, I'm sure that's what the engineer wanted this to look like, but how much money are they going to throw at the problem? So instead they came up with this. Well, you know, some overshoot here. Is it worth cleaning up? How much money do you want to spend on the circuitry to get rid of this overshoot? What quality components do you want to buy to get rid of this overshoot? Undershoot occurs for the same reason. This would be the undershoot right down here. The target was 0%. We wanted it to come right down and then boom, crisply stay off. Instead, we overshot that. Went a little bit negative. Both undershoot and overshoot conditions are followed by damped oscillations known as ringing. This is the ringing. Overshoot, overshoot, then it dampens out. Basically, those are caused by imperfections in components in the circuit design. The bottom line, how much money do you want to spend getting rid of this stuff? Engineers have to look at that. Anybody in here want to be an engineer? There's nothing wrong with it. You got to know what you're getting yourself into, though. Because engineers are given a budget, and they say, you've got to make this circuit, and it can only cost this much. It can only be this big, and it can only cost this much. It's not, we want you to go out and design the best possible circuit to do this. It's like, you got to develop a circuit that could do this, but it can only cost this much money. So engineers have to constantly compromise. Constantly. And because they compromise, this is what we're left with. Circuits that have outputs that look like this stuff. You've got to be able to recognize it. So all of this could be analyzed on the oscilloscope. Wave shaping circuits also include an RC network. Could change the shape of a complex waveform. A differentiator is used to produce a PIP, or peaked waveform, from square or rectangular waveforms. Okay, let me show you an easy way of remembering these. Everybody got this on the board? The thing to remember about my lectures is this is what I lecture on is not nice to know information. What I lecture on is need to know information. This is the kind of stuff that you're going to get on a job interview. They're going to sit you down and they're going to show you a waveform like I just showed you, and they're going to say, what's the rise time, what's the fall time, what's the pulse width? I mean, these are like no-brainer questions that if you can't answer, they're going to hire somebody that can't answer those questions. Okay? The same thing goes with differentiator and integrator. If I had a quarter for every time I was asked about an integrator and a differentiator on a professional exam, I'd have enough for one of those gourmet cheeseburgers probably, and a gallon of gasoline in today's economy, okay? But I've been asked that a lot of times. The thing to remember about an integrator and a differentiator, real simple. Both are made out of an RC, a series RC circuit, okay? Here's my RC circuit, right? Okay. Now, I have two different combinations that I could take outputs. I could take an output, actually three. I could take an output across both of these. I could take an output across my resistor, or I could take an output across my capacitor, right? So here, terminal A, terminal B, terminal C. If I monitor, take an output across A and B, I'm taking the output across the parallel resistor. If I take an output across B and C, I'm taking the output across the voltage across the parallel capacitor. Make sense? Okay. Now, let's take a closer look at what we're putting into the circuit. We're putting a square wave into the circuit. Let me draw a larger version of the square wave. Does everybody agree that that's a square wave? A good likeness of a square wave? How do I know it's a square wave? 50% on, 50% off. I hired Peter Welty. I actually asked him that in a job interview. I had a little circuit spitting out a square wave. I knew it was a square wave. So I gave him a scope meter, Fluke scope meter, and I said, what's coming out of test point 22? He set it all up, untangled the cords. I tangle them all up in the interviews so people get flustered, have to untangle it all. Fires the thing up, he gets a test probe. It's a square wave. And I asked him, what's the duty cycle of that square wave? And he kind of looks up like, duh, 50%. And I knew I had found my man. okay? Because I had PhDs in here that were like, what's a square wave? And they're just in their classes. Well, I got to calculate it out. If it's a square wave, it's 50%. If it's less than 50%, it's a pulse wave. If it's greater than 50%, it's a rectangular wave. Make sense? So, we're applying a square wave to this circuit. What am I going to get across the capacitor? What's the output across the capacitor going to look like? One of the reasons that I drew it on the whiteboard is so we could take a look at that, right? When the square wave, I go from 0 to 100% instantaneously, do I not? What's the capacitor going to do when I go from 0 to 100 instantly? It's going to slow it down. But what's the capacitor going to do in this amount of time right here? Charge. So if I took an output across the capacitor between time 0 and time 1, what would it look like? It would look like a capacitive time constant, would it not? So it would look like that. Do you agree? If the voltage across the capacitor looks like this, what's the voltage across the resistor going to look like? Well, first of all, what kind of a circuit is this? The first thing you should always say is identify the type of circuit. Is this a series circuit or parallel? It's a series circuit. It's a series RC circuit. So if the voltage across the capacitor, and also, I'll give you a hint here, a series circuit is also known as a voltage divider. So if the voltage is going from 0 to 100 over time, what's the voltage across the capacitor going to be doing? This is not a trick question, folks. It's going to be going from 0 to 100%, and then it's going to be going down like this. Because as the capacitor is charging to 100%, the voltage across the resistor was going from 100%, now it's going to 0%. Because remember, if I have 100% here, I've got 0% here. If I've got 0% here, I have 100% here. If I've got 50% of the voltage here, I got 50% of the voltage here, which would be like right about here or here. Does that make sense? Shouldn't be any mystery with this. This is the same stuff we've been talking about. So, from 1 to point number 2, what happens at my square wave? It goes from 100% to 0. And then it holds. What condition is this? Basically off between time 2 and time 3. So, what's the capacitor going to do? It's going to discharge, and it's going to look like a capacitive discharge. When it discharges, where's it going to discharge into? It's going to discharge through the resistor, the only other component in the circuit. So it's going to create POW, a negative voltage, opposite of the force that originally created it, and then that voltage is basically going to go to 0. Make sense? The next square wave pulse comes in, POW, voltage shoots up, a little bit high, a little bit excited there, right? And it's going to come down. The capacitor is going to charge. Square wave is going to shut off. The capacitor is going to discharge. When it discharges, it's going to discharge in the opposite direction and eventually go to 0. And that process is just going to continue to repeat itself. When we take the output across our resistor, across our parallel resistor, it's a series circuit, but I'm taking the output in parallel. I'm attaching my load in parallel with that resistor so that I could get the benefits of being connected in parallel. The same voltage that's developed across this resistor I will feel in parallel with it. Make sense? Be careful with that wording. Am I overemphasizing it? Yes. Why? Because people miss this on a freaking quiz. They miss it on the exam, they miss it in the lab, they miss it when they go out into industry. It's a series circuit, but you're connecting the output in parallel with that resistor. So you get the same voltage across it. When we do that, this is called a differentiator. And I always remember differentiator like in cursive D, I, F, F. See the FF, those sharp points? That kind of looks like FF, the top of my FF. It works for me. If a differentiator has the sharp pointed outputs, or the pip outputs as it says in the book, the integrator will be connected to the parallel capacitor. And these look more like, I don't know, waves in the ocean. I guess if it's a tsunami coming at you or something. But these look more like ocean waves. These are sharp, sharp points. So to get an output across your integrator, we connect across our parallel capacitor. An integrator is used in wave shaping of radio, television, radar, and computers. Basically what we're doing is using the integrator and differentiator to change the makeup, change the pulses, change the output to something that we want. Wave shaping circuits. Does that make sense? If you get screwed up on your quiz, and you will, if you get screwed up on your exam, and you will, if you get screwed up on a job interview, draw this down on scratch paper. It's a series RC circuit. How is it going to behave? When I slam this with a square wave that basically is DC voltage, off, 100%, hold on, off, how's it going to work? It's going to charge a capacitor up, but it's going to take time to charge a capacitor up. As the capacitor is charging, the voltage across the resistor is decreasing. Pretty basic, I think, but I've been doing this a while. But don't let me twist you up. Be able to answer these questions. A clipping or limiter circuit can be used to square off the peaks of an applied signal. They can obtain a rectangular waveform from a sine wave signal. So basically, if you've got a sine wave and you just clip the top of that off, you're basically, boom, like slicing the top of it off. It's kind of going to look like a square wave. Also can eliminate positive or negative portions of a waveform. A limiter circuit can also keep an input amplitude at a constant level. This is very important in broadcasting. Very important in broadcasting. AM radio, AM stands for amplitude modulation. So basically, if you start increasing the amplitude beyond the specifications, you're going to transmit out more power. So back in the day, Dave Niehaus, who's passed away, of course, this past year, when he was calling a Mariners game, somebody knocks it out of the park and get out the rye bread and salami, and he's yelling into the microphone. If they didn't have a limiter circuit, that transmitter, Cairo or Como or whoever was broadcasting the game, would physically transmit out more power than they were licensed by the FCC. So radio stations have these limiter circuits to keep that amplitude constant so they don't broadcast out more power. In FM radio is frequency modulation. If you go over that modulation limit, you're going to alter that frequency beyond the specifications of what the FCC limits you. So these limiter circuits are very, very critical to get the right output levels so that the transmitter transmits the right amount of energy. And it's not just in commercial broadcasting. For a radar system, the same thing. A sonar system, the same thing. A police radar gun, the same thing. It's going to have some limiter circuits in there to prevent too much energy from coming out so that it knows how much to expect to come back. You just can't transmit out. Your cell phone has limiter circuits associated with it. Actually, in your cell phone, the circuits are pretty much dynamic. It's listening to the tower. It knows how far you are. If any of you have ever gone out in the woods or anything, away from urban areas, sometimes your cell phone will do everything it can to stay connected to the cellular network. And if you're on the fringes, it's going to work harder and drain your battery faster, but it's going to stay connected. If you're parked right next to a cell tower, it's going to broadcast only the amount of power that it needs to stay connected, no more, so your batteries will last longer. Cell phones do it a little bit different, but you understand the concept of limiting. Clamping circuit can be used to clamp the top or bottom of a waveform to a given DC voltage. This is commonly used in radar, television, telecommunications, computers. As you know from our studies, we use DC to bias solid-state components. That means the voltage that establishes an operating point to turn a semiconductor device on, right? But the signal, which represents the intelligence, the audio, the video, the whatever, we need to put that on the DC level. So what we're going to do is clamp that to AC signal to a DC level. That's what clamping means. Special purpose circuits include a monostable multivibrator. Has only one stable state. That's why it's called a monostable. Mono meaning one, stable state. It produces one output pulse for each input pulse. A bistable multivibrator has two stable states, and they're called flip-flops. And we're going to talk more about these bistable multivibrators in the future because they are the fundamental building block of digital circuits. Because in digital, as you'll soon find out in our next lecture, we deal with two stable states, on and off. All the magic in digital is brought to you by two stable states. In summary, waveforms can be changed from one shape to another using various electronic circuits. The frequency domain concept holds that all periodic waveforms are made of sine waves. Periodic waveforms have the same wave shape in all cycles. Sine waves are the only waveform that cannot be distorted by RC, RL, or LC circuits. According to the frequency domain concept, waveforms consist of the fundamental frequency plus combinations of even or odd harmonics or both. A square wave consists of the fundamental plus an infinite number of odd harmonics. Sawtooth waveform consists of the fundamental frequency plus even and odd harmonics crossing the zero reference line 180 degrees out of phase with the fundamental. Periodic waveforms are measured from any point of the cycle to the same point on the next cycle. Pulse width is the length of the pulse measured at the 50% point. Duty cycle is the ratio of pulse width to period. Rise time of a pulse is the time it takes to rise from 10% to 90% of its maximum amplitude. Fall time is between 90% and 10%. Overshoot, undershoot, and ringing are undesirable in a circuit and exist because of imperfect circuits. An RC circuit can be used to change the shape of a complex waveform. If the output is taken across the resistor in an RC circuit, the circuit's called a differentiator. If the output's taken across the capacitor, it's called an integrator. Clipping circuits are used to square off the peaks of an applied signal or to keep an amplitude constant. Clamping circuits are used to clamp the top or bottom of a waveform to a DC voltage. In a monostable multivibrator, one shot produces one output pulse for each input pulse. Bistable multivibrators have two stable states. And we also have what's known as a Schmitt trigger. It's a special purpose bistable multivibrator that's used for cleaning up wave patterns. It's one of the things too on clipping and limiting. Do you ever notice when you listen to an AM radio station, specifically AM radio stations, doesn't everybody like on Cairo kind of sound the same? Doesn't everybody on KVI kind of sound the same? Como? Don't they all kind of sound the same? That's really a function of the electronics that they're using. It's a function of the microphones that they use, the studios that they use, the clipping circuits that they use, the limiting circuits that they use. Some radio stations in the past have even used a little bit of reverb that they feed everything through, and then they transmit that, so that all kind of has a unique sound to it. I don't know if you know this about me, but before one of my first jobs, I worked in radio. I worked in AM radio at a radio station in Connecticut. And actually, I found some old air checks of myself, recordings. You'd never know it was me. I mean, I sounded good. I sounded really good, because you're speaking into a high compression microphone and you're getting run through that electronics. And it used to be fun. You put the headset on, and next thing you know, you've got the magic voice. You know, and it was no magic voice. It was just the electronics that your voice was being run through. Same thing actually happens in the recording industry. Different studios have different idiosyncrasies because of the electronics. Some of the purists out there, the audiophiles that go out there, you know, if you're a big, you know, Led Zeppelin fan, and you know, there's a specific album that really rocks your world, you know, some of the purists go out there and they know what studio this was mixed at, and they know what monitors were used in the studios in the mixing process. So if you ever want to listen to that music as it was originally intended, you need to be listening out of the same electronics and the same speakers that it was originally mixed down at. You're listening to it on a headset, it's not going to be the same experience. If you're listening on a set of Radio Shack speakers, it's not going to be the same experience. So the same thing is, like I say, with radio. Every station's going to end up with its unique idiosyncrasies. And quite frankly, back in the day, radio has really changed now. You know, it's a whole different ball of wax than it used to be. It used to be highly competitive. A lot of these radio stations used to go after a unique sound. Unique sound, so that people would, you know, get used to that and tune into that. And now everybody's like, what is it? What's the online? You listen on your smartphone. Pandora, yeah, your Pandora. You know, people aren't even subscribing to satellite radio anymore. They're doing Pandora on their phone and plugging that into their audio system. Me, I'm a satellite guy. Any questions on anything we covered in wave shaping? Okay, let's go ahead and take about a 12-minute break at 25 after 5. We're going to start up with digital.